Hello everyone and welcome to our math studio. In this first episode, we are going to learn the basic rules of indefinite integrals. We will cover algebraic, trigonometric, exponential, and logarithmic integrals, as well as inverse trigonometric integrals. I hope you find this lesson helpful. Let's get started. All right, let's start our lesson with the indefinite integral. Essentially, the indefinite integral is the inverse operation of differentiation. This means we need to find the original function that produced the result. As you can see here, if we take the derivative of f of x, it becomes f prime of x. And if we integrate f prime of x, it becomes f of x. Therefore, it is very important to have a strong command of derivative rules. Your grasp of differentiation should be strong enough that you often know the answer intuitively without even calculating the integral. Let's start with the basic integration rules. Mathematically, we see that the integral of f prime of x dx equals f of x plus c. In this formula, the dx specifies the variable of integration. As you recall, when taking derivatives, we always had to specify the variable. For instance, f prime of x indicated that x was our variable, or dy over dt meant we were differentiating y with respect to t. Similarly, in integration, the dx clearly defines the variable of integration. Here, f of x represents the original function, also known as the antiderivative. We are essentially asking what function did we differentiate to get this result. That is why we call it the original function. You will also notice the plus c. I will explain the significance of this constant shortly. Now let's move on to the basic rules of indefinite integrals. The first rule is the integral of k dx. The integral of k dx. So let's look at the integral of a constant. For instance, ask yourself, what function has the derivative of 5? We all know the answer is 5x. However, someone might say it's 5x plus 2, and another person might suggest 5x plus 10. As you can see, the derivative of all these examples is 5. That is why the integral of 5 is 5x plus c. In general, the integral of k dx equals kx plus c. This is the rule for the integral of a constant. Let's look at the sum and difference rule. You might recall from differentiation that we could take the derivative of each term separately. The exact same rule applies here. To integrate a sum or difference, simply find the integral of each function individually and then add or subtract the results. Rule number 3. This is the most fundamental integral we will deal with, the integral of x raised to the power of n. To integrate x to the power of n, simply add 1 to the exponent and then divide by that new exponent. Therefore, the integral of x to the n dx equals x raised to the n plus 1 over n plus 1 plus c. It is important to note that for this rule, n cannot be equal to negative 1. Why? Because the denominator will become 0. Now, you might be asking, what if n is negative 1? What do we do then? We will cover the case where n equals negative 1 later in this course. Now, for the final rule of this section, the constant multiple rule. Let's look at the integral of k times f of x dx. When a function has a coefficient, we do not integrate the coefficient itself. Remember that in differentiation, we did not apply the derivative to the constant coefficient. We simply kept the constant and differentiated the function. The same rule applies here. So if you see the integral of k times f of x, you can simply pull the constant k outside of the integral sign, then integrate f of x, and finally multiply the result by k. So go ahead and do the multiplication. Now, let's apply these rules to some examples. Whenever you feel confident, I encourage you to pause the video, work out the problem yourself, and then resume to check your answer with me. We begin. Let's start with a simple polynomial example. The integral of x squared minus 3x to the fourth plus 5 dx. For x squared, as I mentioned, we add 1 to the exponent and divide by that new number. So it becomes x cubed over 3. Next, we bring down the minus sign. Now let's integrate 3x to the fourth. We simply keep the coefficient 3. We increase the power of x to 5 and divide by that same number. So it becomes 3x to the fifth over 5. Next, we have plus 5. Since 5 is a constant, its integral becomes 5x. And finally, we add plus c, our integration constant. Let's move on. The next example is x squared times the square root of x. Here is a crucial point regarding integrals. Unlike differentiation where we had formulas for products and quotients, in integration there are no such formulas for multiplication and division. That means unlike derivatives, you cannot apply a rule like the integral of the first times the second plus the integral of the second times the first. That rule simply does not exist here. Why is that? And this is exactly what makes integration more challenging than differentiation. Therefore, when integrating, we must try to eliminate multiplication and division. This is a key strategy. Whenever you see a product, be certain that you need to get rid of it by simplifying the expression first. Let's consider the integral of x squared times the square root of x. As you can see, there is a multiplication here. We cannot integrate this expression directly. So how do we handle this? I will simply rewrite the square root of x as x to the power of 1/2. Since the bases are the same, we simply add the exponents. We combine x squared and x to the power of 1/2. 2 plus 1/2 equals 5/2. So the result becomes x to the power of 5/2. Notice that the multiplication is now eliminated. Next, for the cube root of x, I rewrote it as x to the power of 1/3 plus 5. Okay, so now x is raised to the power of 5/2. What was the rule that we agreed upon? We need to add 1 to its exponent. So the first term becomes x to the power of 7/2 over 7/2. Following that, we get x to the power of 4/3 over 4/3. For the constant term, the integral is simply 5x plus c. Now, to make the answer look neater, since the original problem was given in radical form, I converted the final answer back into radicals as well. It becomes a 2/7 times the square root of x to the 7 minus 3/4 times the cube root of x to the 4th plus 5x. Now let's move on to the next example. Here we have a division again. Let me give you a quick tip. At this point, if you would like, feel free to pause the video. Now try to solve the problem on your own. The integral is x cubed minus 4x over the square root of x. My suggestion is to rewrite the square root in the denominator as a power. Write the denominator as x to the power of 1/2. Since we move it up to the numerator, it becomes x to the power of negative 1/2. Now simply multiply the expression by this term and try to find the integral on your own. Well, I hope you were able to solve it on your own. If not, that is perfectly fine. These are just our initial examples. Soon you will handle them with ease. So we write x to the power of negative 1/2 and distribute it into the parentheses. Since the bases are the same, we simply add the exponents. So the expression becomes x to the power of 5/2 minus 4 times x to the power of 1/2. Now we integrate, we get x to the power of 7/2 over 7/2. Next, for the term minus 4, we simply keep the constant and multiply it by x to the power of 3/2 over 3/2. Finally, I simplified the fractions and converted the answer back into radical form. Let's move on to the next example. We have the integral of the quantity x squared minus 4 or squared times the square root of x. I am sure you know what to do. We simply start by rewriting the square root of x. We rewrite the radical as x to the power of 1/2. Now we need to eliminate the parentheses. Since we cannot integrate this directly, we must first expand the squared term and then distribute the x to the power of 1/2. I encourage you to pause the video right here, work it out yourself, and then resume to check your final answer with me. Multiply x to the power of 1/2 by the terms inside. Since the bases are the same, we simply add the exponents. The terms are combined. Now we have simple powers of x. This is the main rule. We add 1 to the power, then we divide by that new number. Finally, I wrote the answer back in radical form. So the first thing we learned is we can't integrate products or quotients. We convert products and quotients from their current form, then integrate them using the rules of integration. You might ask, can all products and quotients be handled this way? No, it's not going to work. That's why they'll teach you other methods later on. But remember, our first and main priority when calculating integrals is to eliminate multiplication and division. Someone can truly be a good integrator if they have a very organized mind. What this means is that when you're given a problem, you'll immediately know what the very first priority is for solving this particular type of question. All right, let's continue with the work. We have another exercise, the integral of x squared over the cube root of x plus the 5th root of x over the square root of x minus x. Also, as agreed, we must eliminate these fractions. We rewrite the entire expression in power form, then we integrate each term one by one. Once again, I strongly recommend you pick up a pen. Try to solve these problems in your notebook. Please pause the video right now, then come back to check the solution with me. I hope you have been able to solve this question, but if not, it's no problem at all. I'm sure that in the next questions, you will solve them much more easily. We wrote the expression in exponential form. We simplified the terms to get x to a specific power. Then we integrated and converted the answer back to radical form. We are now finished with algebraic expressions. So let's move on to trigonometric integrals. We will now add trigonometric expressions to the mix. Remember, integration is simply the reverse of differentiation. So we said the integral is the inverse of the derivative. It's also very helpful with trigonometric functions to ask what function was differentiated to get these. Naturally, you should have a certain level of proficiency in basic trigonometric relationships. Look at the integral of sine ax. To solve it, we asked which function was differentiated to give us sine. When we are differentiating, we always wrote the derivative of the arc. That is, we would place an a behind it. But since we are in integration, as you can see, 1 over a is placed behind it. So we know that the derivative of the cosine function is negative sine, and because integration works in the opposite direction, the integral of sine will consequently take on a negative sign this time. Therefore, the integral of sine becomes negative 1 over a times the cosine of x plus c. Now, the integral of cosine x. The integral of cosine x is 1 over a times sine x plus c. The integral of 1 plus tangent squared. 1 plus tangent squared is extremely important in integral calculations. And since many trigonometric identities lead to 1 plus tangent squared, it's good to learn its formulas right here. 1 plus tangent squared equals 1 over cosine squared. Therefore, the integral of 1 plus tangent squared is the same as the integral of 1 over cosine squared. 1 over cosine squared itself is equivalent to secant squared. Perhaps you haven't heard the term secant very often. We define 1 over cosine as secant in trigonometry, and therefore 1 over cosine squared is equivalent to secant squared. What will be the integral of all of these expressions? What was the original function whose derivative became 1 plus tangent squared? You surely remember that the function we differentiated was tangent. However, because of the coefficient a, the answer is 1 over a times tangent ax plus c. We will see this integrand often, appearing in 3 forms: 1 plus tangent squared, 1 over cosine squared, or secant squared. We'll apply this very same rule to the cotangent function. The integral of 1 plus cotangent squared of x. Now, 1 plus cotangent squared is equivalent to 1 divided by sine squared. 1 divided by sin, we call it cosecant. So the integral of dx over sin squared is equivalent to the integral of cosecant squared. Well, what was it that, when differentiated, became 1 plus cotangent squared? It's negative cotangent x. Okay, now let's solve some simpler examples to see how trigonometric relationships enter into the integral. The integral of negative sine of 2, x plus cosine x plus 7. Okay, we can both say what it was that its derivative became sine, which can be a clue for us, and we can also use the relationships that we have memorized. The integral of negative sine to x, since its argument has a coefficient of 2, according to our established rule, we invert the coefficient and place it at the beginning, so it becomes 1/2 cosine to x plus the integral of cosine, which, as we know, is sine. It also has a constant term at the end, which is the number 7, and as we previously agreed, that becomes 7x plus c. Alright, let's proceed to the next example. The integral of cosine 2x divided by cosine plus sine. As you can clearly see, we're once again presented with a fractional integral. Now, as we've discussed, we cannot directly integrate an expression that is in fractional form. Therefore, it's essential that I transform this expression to remove its fractional nature. One of the fundamental formulas that we all learned during our high school years was that cosine of 2x is precisely equivalent to cosine squared minus sine squared. If I write this relation and then factorize the expression using the conjugate identity, here we see that cosine x minus sine x multiplied by cosine x plus sin x. If we then simplify the cosine plus sin term in both the numerator and the denominator, the fraction will very easily cancel out. Then we will have the integral of cosine minus sin, and with the help of the relationships that we have learned, the result of the integral will be very easily obtained. Let's move on to the next example. I truly hope that you will try to solve this problem on your own first, and then come back to check my solution. I am going to guide you through the integral of sine 2x divided by cosine x. The integral of sine 2x divided by cosine x is a fraction, so this fraction must be eliminated. Trigonometric identity that will help us is the sine of 2x formula. You had learned the sine of 2x back in your high school days, that it equals 2 sine x cosine x. You just need to use this identity and you can solve it very, very easily. Well, I hope you were able to solve it on your own. We have 2 sin x cosine x in the numerator. The cosines cancel each other out. What remains is the integral of 2 sin x, which very easily gives us negative 2 cosine x. Let's move on to the next example. We'll try step by step to raise the level of the questions, and as we go higher, your mastery will definitely increase. Let's move on to the next integral, the integral of 1 plus sine 2x all over sine plus cosine. We can write the number 1 as sine squared plus cosine squared. Again, take a look. What is my primary goal here? It is to ensure that this fraction is completely eliminated. If I write 1 as sine squared x plus cosine squared x and then expand sine 2x, the numerator becomes the perfect square, sine x plus cosine x all squared. The numerator and denominator simplify very easily. What remains is the integral of sine x plus cosine x, which you have surely learned how to calculate. Let's move on to tangent and cotangent. The integral of tangent plus cotangent multiplied by sine 2x. If your understanding of trigonometry was strong back in high school, you would know that tangent plus cotangent itself has a specific trigonometric formula. However, you might not recall it at this moment. Well, then just easily write down the tangent function. Sine of x divided by cosine of x, write cotangent as well, cosine divided by sine. And sin 2x, which we're dealing with for the third time today, I'll write sin 2x as 2 sin x cosine x. Okay, I'll find a common denominator inside the parentheses. What do we have in the numerator? Sin squared plus cosine squared, which equals 1, and we simplify the sine cosine outside. You see, there's nothing left. That integral of 2 dx just became the result of the integral so easily. 2x plus the constant c. All right, let's take a look at the next example. Integral of sin x times cosine t dt. Here, I just want to remind you of one important point. I chose a very simple question for this, just so you understand what that dt actually does. I've written down the integral of sine x times cosine t, and notice this time it's dt. This is probably the very first question you're seeing where the differential is dt. So what exactly does this dt notation actually mean? It simply means that the variable of integration for this specific integral this time is not x. Instead, the variable we're integrating with respect to is t. So sin x is treated like a number. So I'm not going to do anything with sine x. The integral of cosine t will become sine t, and sine x acts as its coefficient. This was an interesting example for you to see the application of this dt. Although we will definitely see many more questions about this further on, it was certainly not without its benefit to have seen this type of question here. All right, let's move on now. The integral of tangent squared. Many of the relationships and also the examples we're solving right now will later appear mixed in with other problems. This means you might later encounter a very large integral where one part of it is tangent squared. That's why we're going to calculate these very common relations here as practice exercises. So I ask myself, what was the function whose derivative became tangent squared? This looks very familiar. If it were 1 plus tangent squared, I would have been happy. Because 1 plus tangent squared, its integral just becomes tangent. But it doesn't have that one. So what am I going to do? I'm adding a 1 to it, and then I'm subtracting a 1 from it. This means instead of just tangent squared, I wrote 1 plus tangent squared minus 1. So the problem is now solved. Now, what function has a derivative of 1 plus tangent squared x? It is simply tangent x. Then we have the integral of the constant 1, which becomes x. So very easily remember this common result, tangent x minus x plus c. We continue. The integral of 3 dx, all divided by 1 minus cosine squared. All right, we're looking at the integral of a fraction once more. We need to eliminate this fraction. It's quite clear that the expression 1 minus cosine squared is something you've known since childhood to be equal to sin squared. So the question became the integral of 3 over sin squared. So it was among the initial relations. What was it whose derivative became 1 over sine squared? If you recall, I mentioned that 1 over sine squared is the same as 1 plus cotangent squared. What was it whose derivative became 1 plus cotangent squared? Excellent. So it is negative cotangent x. And with that coefficient, the final result is minus 3 cotangent x plus c, which is always with us. Now let's move on to the next example. First, I'll explain the integrals of e and natural log, and then we'll proceed. As an engineering student, you absolutely must be familiar with e and ln, which are crucial engineering tools. E is Euler's number, which is 2.7, and I've explained this in much more detail on my Instagram page. But for now, we'll consider the number e to be 2.7. Ln is also a logarithm whose base is the mathematical constant e, and it's denoted by ln. You studied logarithms back in high school, didn't you? A logarithm whose base is the number e is specifically called ln. Because it's so widely used and important, it has its own special name, or it's also referred to as the natural logarithm. The derivative of e raised to a power is the derivative of its exponent multiplied by itself. This means if you see e to the power of x squared, its derivative becomes the derivative of x squared, which is 2x times e to the power of x squared. Now we want to take its integral. For now, we will study the integral of e to the power of a first degree expression together. As we move forward and become more proficient, we will also see the more challenging problems together. But for now, for the integral of e to the power of ax plus b, we'll simply invert the coefficient of x in the exponent. We bring it to the front, it becomes 1 over that coefficient. And we write it down exactly the same. You see, the integral of e to the power of ax plus b dx becomes 1 over a times e to the power of ax plus b, the integral of dx over ax plus b. If you remember, on the page where I told you about integral relationships, I said n cannot be minus 1. So observe that we have a first degree expression in the denominator. X plus b is indeed a first degree expression. How do we integrate something like this? First, we need to recall the derivative of natural log. Remember, the derivative of natural log of u is u prime divided by u. This really helps us integrate fractions where the denominator is first degree. Let's see it together. What is the integral of dx over ax plus b? What's the x coefficient in the denominator? The answer is a, so we write its reciprocal in front of the expression. This means we write 1 over a multiplied by natural log. Inside the log, we place the denominator exactly as it is, usually within absolute value signs. As you surely learned in high school, logarithms and of course natural log cannot have a negative value inside them. That is strictly forbidden. That's why they put this in absolute value. But even if you don't, no one will fault you for it. Don't worry. So for the integral of dx over ax plus b, it's the reciprocal of the x coefficient in the denominator, followed by ln, and we write the denominator exactly as it is. Naturally, now it's time for an example. Let's do an example. Alright, for our first example, we have the fraction dx over 2x plus 1. Its denominator is of the first degree. This is giving us a hint that we should use the natural logarithm ln. What's the denominator's x coefficient? 2. So we write its reciprocal, which is 1/2, then natural log, and I write the denominator exactly as it is. The natural log of 2x plus 1. I put it inside an absolute value, I mentioned that, but I won't dwell on it too much. Now let's move on to our next example. The integral of x plus 3, all divided by x dx. Further along in this series, I will teach you about integrals of fractions in great detail, but for now, just keep it in the back of your mind. We cannot directly integrate a fraction whose numerator's degree is greater than or equal to its denominator. That's why in this problem, since the numerator and denominator degrees are equal, I'll first either divide the numerator by the denominator, or because it's very easy to separate, I'll separate it for now. So x plus 3 all over x can be separated. X divided by x becomes 1 plus 3 over x. Now I start integrating. The integral of 1 is x. And for the integral of 3 over x, when we have a fraction where the denominator is first degree, what method should we use? The natural log. Since the coefficient of x in the denominator is 1, we simply keep the 3 as the coefficient. So the answer is 3 times the natural log of x plus c. All right, let's move on to our next example now. We're going to take the integral of this one as well. The integral of e raised to the power of 3x minus 1 dx. Now, how did I say we integrate e? The coefficient of x, its power, we take the reciprocal. What is the coefficient of x? 3, the reciprocal, 1/3. We write exactly the same e, 1/3 e to the power of 3x minus 1. Let's solve a slightly harder example. The integral of e to the power of 2 times natural log of x dx. At this point, we need to remember some fundamental logarithmic rules. What exactly are we referring to here? In logarithms, we had learned that a coefficient in front of the log can be converted into an exponent. This means we can take the 2 and move it to become the power of x. So it effectively becomes e raised to the power of ln x squared. This is the concept you might recall from high school logarithm lessons. The exponential and logarithmic functions are inverse operations of one another. This means that when they are applied consecutively, one after the other, they effectively cancel each other out. E and ln are inverse functions of each other, which means that e raised to the power of the natural logarithm of any given value would simply result in that very same value. E and ln effectively cancel each other out. This is precisely why when you observe e raised to the power of ln of x squared, the e and ln terms have cancelled, leaving only x squared. So what then is the integral of x squared? This one is quite straightforward. It's x cubed divided by 3 plus c. Let's proceed to the next example now. Perhaps it would be a good idea for you all to try solving this one. It's ln of e raised to the power of cosine x. Let me offer a small hint. As I've previously stated, ln and e are inverse functions. So you saw that natural log and e cancel each other out. So what is left? Simply the integral of cosine x dx. This is now very straightforward for you. The answer is sine x plus c. Next, we are going to explore inverse trigonometric integrals together. First, you need to understand what inverse trigonometric functions are, then learn their derivatives and then their integrals. If I were to give you a general overview, inverse trigonometric functions are just like the inverse of any other function. What exactly were inverse functions? We used to say that x and y simply swap places in an inverse function. If we apply this to inverse trigonometric functions, for example, to construct the inverse of sin, it is referred to as arcsine x. It is also written as sine to the power of -1. But be careful, that power is just a symbol for the inverse function, not a real exponent. Sine to the power of -1x. So, what we're going to do here is, first I'll teach you the derivatives of arcsin, arccos, and arctan. What is the derivative of arcsin u? It is the derivative of its argument, that is u prime, divided by the square root of 1 minus u squared. So that is the derivative for arcsin. For arccosin, the only difference is a single negative sign. Therefore, the derivative of arccosin u is negative u prime divided by the square root of 1 minus u squared. Alright, so what exactly is the derivative of the arctangent function? It's u prime divided by 1 plus u squared. And for the derivative of arcotangent, it's negative u prime over 1 plus u squared. I highly recommend that you spend some time practicing these formulas so we can then more easily apply them when we work with integrals. If we want to get to the integral formula itself, we arrive at this, the integral of dx over the square root of a squared minus x squared. As you can clearly see, the result of this integral has become the inverse sine of x divided by a, or alternatively, it's also known as the arcsine of x over a. Now, what about the integral of dx divided by a squared plus x squared? What does this one become? The result is 1 over a times the arctangent of x over a. As you can clearly observe, the formula for arcsine does not include a 1 over r coefficient at its beginning, whereas the formula for arctangent distinctly features this 1 over r coefficient. Please do not mistakenly assume that we have forgotten to place the 1 over r term before the arcsine expression. No, the arcsine function inherently does not possess a 1 over r factor, but the arctangent expression, on the other hand, certainly does include a 1 over a term. Let's go ahead and solve a few examples. Naturally, at first, solving inverse trigonometric examples might be a little challenging for you, but with consistent practice, it will definitely improve. So please don't worry about it at all. Let's move on to our very first example. We have the integral of dx over the square root of 3 minus x squared. Look at the integrals form. It's the square root of a number minus x squared. This is the third step of our work, so I can make it resemble the arcsine integral formula. I have rewritten the number 3 under the radical. It becomes the square root of 3 squared. Now go ahead and compare it with the formula. In the formula, as I told you, we had the square root of a squared minus x squared. So ask yourself, what has come in the place of a square root of 3? Excellent. So I'll just use the formula. It's quite simple. This will be arcsine x divided by a. What was a again? It was the square root of 3. Therefore, it's arcsine x divided by the square root of 3. You also have the option to rationalize it. The integral of dx over the square root of 9 minus 4x squared. Look at what I've done here. I put a coefficient for x squared right under the radical. So what exactly am I going to do now? I'm going to get rid of this coefficient. I'll grab that 4 and just yank it right out from under the radical. Actually, I factor out a 4 from under the radical. I force it out. Pay attention. When 4 comes out, it's because a radical is applied to it. What comes out then? A 2 will appear. We've mistakenly observed students attempting to extract the 4 on their own, and as a result, all their efforts were wasted. Therefore, I'm going to factor out the 4 from under the radical. Since I want x squared to be the coefficient under the radical, I've taken the 4 outside. And now, pay close attention here, because you must also factor out the number 4 from the 9. So, I'll just write it very simply as 9 over 4. This means we now have the square root of 9/4 minus x squared, which has taken the form of a squared minus x squared. The 4 came out as a 2, so the 2 is in the denominator. I will make it a coefficient, 1/2. So we get 1/2 times arcsine of x over 3/2. Oh, but be careful. I have seen students get excited here, thinking they are done, and that they have solved it correctly. Instead of paying attention to 9/4 squared, they unconsciously wrote x divided by 9/4. Be careful, 9/4 squared means what number, when squared, becomes 9/4? It's 3/2. So this is 3/2. I would have easily written x over 3/2. Now we've inverted it, and it's become 2/3 x. Let's move on to the next example. This time, it doesn't have a radical. As you can see, it's the integral of 5 dx over 4 plus 9x squared. This time, the form it takes is quite similar to the integral of arctangent. However, the arctangent integral I had mentioned to you earlier, its denominator, x squared, had no coefficient. That's not a problem. I'll simply extract the coefficient from it. How did I achieve that? I factored out a 9 from the denominator. There was a coefficient of 5 in the numerator. I also brought that out from the expression. That's why I wrote it as 5 ninths. And the 4 in the denominator then became 4 ninths plus x squared. All right, now the overall form of this expression looks like an arctangent. This 4 ninths is the same as 2/3 squared. Its form became similar to dx over a squared plus x squared. Pay attention, I'm going to use the arctangent formula. I told you, what does arctangent have extra? A 1 over a. Don't forget this 1 over a. That's why 1 divided by 2/3, meaning 3/2, also appeared in front. So it has become 3/2, the coefficient 5 ninths of arctangent x over a, and inside the arctangent we wrote 3/2 as the coefficient of x. We want to solve some mixed examples together. It's a series I've shown you from the start, and I want you to identify them. Please pause each one first, think about the problem. If you find you can't solve it, review your previous notes. I'll review the examples we solved together and use them to help solve these new ones. Don't rush to see how I solve it. Think for yourself first. You must dedicate time to solving math problems. As the late Mariam Mirzakhani, the great Iranian professor, used to say, the beauty of mathematics only shows itself to more patient followers. You must be patient when solving math problems. Okay, for the first example, we have the integral of 1 over sine squared x times cosine squared x. Let me give you a hint. You need to get rid of this fraction. I want everyone to pause and think for themselves. Take your time. I hope you managed to solve it. If you did, that's great. If not, don't worry about it at all. It's perfectly fine. With a bit of practice, you'll get the hang of it and solve future questions much more easily. All right, let's tackle the integral of dx over sine squared x times cosine squared x. To handle this fraction, let's try a different approach. Notice the product of sine and cosine in the denominator. This reminds us of the double angle formula. We know that sine x times cosine x equals 1/2 sine 2x. Since our terms are squared, we can substitute them with 1/2 sine 2x all squared. This formula is a very suitable method. Keep it in mind. Now, regarding the integral of dx over sine squared of 2x, you haven't forgotten what 1 over sine squared is, have you? I mentioned it in the very first lessons of trigonometry. Remember, 1 over sine squared is that identity equal to 1 plus cotangent squared. The 1/2 squared becomes 1/4. And since it's in the denominator, when we bring it up to the numerator, it flips and becomes a 4. Now, regarding the integral of dx over sine squared of 2x, you haven't forgotten what 1 over sine squared is, have you? I mentioned it in the very first lessons of trigonometry, remember? 1 over sine squared is that identity equal to 1 plus cotangent squared. So ask yourself, what function has a derivative that equals 1 plus cotangent squared? Negative cotangent, that's right, excellent. This gives us a negative 1/2. Now remember the coefficient we had, it was 4. So 4 times negative 1/2 gives us negative 2, which means the final answer is simply negative 2 cotangent of 2x. Now let's move on and take a look at another example together. We'll examine the integral of sine x times tangent squared x. Yes, you absolutely must solve it first. So go ahead and pause the video right here. Go ahead and start solving this question with confidence. Feel free to look back at the previous pages. Just do as much as you can. Try to go one step further than the previous question. That's it. I really hope you were able to solve it. Let me tell you something important. Some integral problems can actually be solved by multiple methods. This means you might use one specific technique or perhaps a completely different approach, and there is absolutely no problem with that. In fact, sometimes the final answers might even look completely different. Sometimes I mention other methods, but other times I stick to the common one. However, it would be much better if you could find a different approach using your own creativity. That is surely correct as well. Don't forget, there's an important way to know if we found the integral correctly. And what is that? Simply take the derivative of the answer you obtained. If you take the derivative and it matches the original function, then you solved it correctly. So what are you worried about? It's perfectly fine if your method differs from mine in some questions. All right, let's move on to the question. We're looking at the integral of sine x times tangent squared x. So I rewrote the tangent part. We know tangent is sine over cosine. And since it was squared, I wrote it out as sine squared over cosine squared. This gave us the integral of sin x times sin squared x all over cosine squared x. Then I rewrote the sin squared in the numerator. I changed it to 1 minus cosine squared. This is the most basic formula in trigonometry. It was probably the very first formula you learned back in the early days. Sin squared plus cosine squared is 1, right? So sin squared becomes 1 minus cosine squared. That's exactly what we wrote in the numerator. Now notice that we still have sin x multiplying the fraction. So let's split the fraction itself. It becomes sin over cosine squared minus cosine squared over cosine squared. In that second part, the cosines cancel out. So what is left? That gives us just sin x. Now, what do we do with the continuation? The integral of sin over cosine squared is extremely useful. I'll actually ask you to memorize it later. I'll write the denominator as cosine times cosine, meaning it becomes sine over cosine times 1 over cosine. When you divide a sine by a cosine, you get a tangent. 1 over cosine remains. What is it? Secant. So it becomes the integral of secant times tangent. You might not know the formula. That's perfectly fine. Unfortunately, the derivative of secant was removed from high school textbooks. That's why it might be a bit tricky for you to find the answer here. The derivative of secant is proven very, very easily. It is simply secant times tangent. So what did we just establish? The derivative of secant is secant times tangent. So what would the integral of secant times tangent be? So what is it whose derivative becomes secant times tangent? It is secant. Well done. Memorize the integral of secant times tangent as a very important formula. The answer is simply secant. And regarding the sine part, you've mastered this. The integral of negative sine is positive cosine. Anyway, let's continue. The integral of x to the fourth over x squared plus 1. Anyway, let's continue. The integral of x to the fourth over x squared plus 1. I previously mentioned a key point. The degree of the numerator shouldn't be greater than or equal to the denominator. But in this question, my numerator's degree is greater. So what do? Nothing complicated. I'll divide the numerator by the denominator to resolve the issue. So I divided x to the fourth map by x squared plus 1. So I don't know which grade you were in, but for at least 4 or 5 years, you've known how to divide polynomials. In case you've forgotten, let's review it. I divided the numerator x to the fourth by the denominator x squared plus 1. And what was the quotient? It turned out to be x squared minus 1 with a remainder of 1. So how do we separate the fraction? We always say start with the quotient. So we have x squared minus 1, and then we add the fraction part. We will not make any changes to the denominator. It stays exactly the same. Simply write down the denominator x squared plus 1, and we place the remainder directly into the numerator. So what exactly has occurred here? The fraction with the oversized numerator is gone. It's been converted into a form where the numerator is no longer greater than the denominator. Now I can comfortably proceed with the integration. The integral of x squared becomes 1/3 x cubed, minus the integral of 1, which becomes minus x, plus the integral of 1 over 1 plus x squared. Yes, its integral is exactly arctan x. This was a good question. It was one of those problems that had a really solid level. Alright, my friends, well done on your hard work. The introductory integral section is now complete. To truly master this part, you definitely need to solve these exercises repeatedly. And please don't worry if you've seen the solutions once, but still can't solve them independently yet. Patience and perseverance in math are what truly pay off. Rest assured, if you solve these problems a few more times and find similar ones in your university textbooks to practice, you will achieve mastery. The next lesson is heavily dependent on what we learned here. I'll see you in the next part very soon. Remember, math is all.